So I will tell you how we use machine learning for heterogeneous catalysis to do tasks like structure predicting, to do kinetic modeling, and ultimately with the goal to design new and better catalysts. So just a brief introduction to me and what I'm interested in. I have two main research interests, and the first one is heterogeneous catalysis, which is what I will focus on today. And here we are interested in the conversion of CO2 to valuable products. This could be products like, let me just get a pointer here, like methanol, CO, methane. We mainly do thermal catalysis, but also a little bit of electrochemical. And my other main research interest is astrochemistry, and here we're interested in also a type of catalyst, but a very different one. So out in these dust clouds, in gas clouds in space, you have these dust grain particles that are believed to be catalysts for the formation of various molecules, some that may be relevant to life. So I'm a co-PI in the Center for Interstellar Catalysis, which is a center of excellence at Aarhus University that's funded by the Danish National Research Foundation. But for today, I'll talk about CO2 conversion, and here's some of the materials we are interested in for that. So we have done some work on metals and surface alloys. Some of this dates back to my time as a group leader with Carsten Reuter, when Ben was a PhD student that worked on this. Raphael is a postdoc in my group who has taken over some of these activities. We've also done some work on oxides, doped oxides, specifically doping zirconia with different other elements. I'll have to skip that, unfortunately, today. But I do want to show you some of our work we did with metal oxide interfaces. So this is work done by Luke, who was a PhD student, now a postdoc in my group, and Marius, who's currently doing his PhD in my group. So first of all, to the alloys, we're specifically interested in single atom alloy catalysts, and the reason that they are interesting is that, first of all, there are some very nice experimental works where people have synthesized these very dilute alloys where you have one element, for example, platinum here, that is present as single atoms within another host metal, like copper, for example. And it has been shown that you can get some very interesting catalytic properties, for example, for this reaction here that they studied with a much higher activity. And there's also been theoretical work on these systems here with density functional theory, where it has been found that they can do some interesting things. They can break linear scaling relations. So linear scaling relations is this sort of observation that when you relate the reaction energy of a given step, in this case it's methane dissociation with its activation energy, well, many materials sort of follow on a line here. But these catalysts, they can break these relations, so they can have a quite low activation energy at the same time as a weak binding. And this is very interesting in catalysis because you have this Sabatier principle, which states that there's sort of an optimum in the bond strengths where you either get limited by desorption of products or by the activation of the reactants. And the reason you have these volcano plots or Sabatier optimum here is essentially because of the existence of scaling relations. So the very interesting aspect here is if you were able to break scaling relations, then you may in principle be able to design catalysts that could go beyond this Sabatier optimum. Now on the downside, in catalysis, typically screening has been carried out using these linear scaling relations. So then we need new methods to screen catalysts if we cannot rely on these anymore. And this is essentially where machine learning comes into the picture in my work. So instead of relying on the scaling relations, we could rely on machine learning for generating the input to do our kinetic models. So Let me first of all explain sort of what is a microkinetic model in catalysis. So we do mainly mean field type models, so known as rate equations, and essentially you then solve these coupled differential equations that have this form here at some given experimental conditions, the temperature here that enters the exponential, and the gas phase pressures of the species. And then you solve these for the steady state coverages, which give you then the rates. And you can then also, if you're interested in methanol formation, then you can report the activity as this turnover frequency. So how many molecules do we produce per site of catalyst per second? Now, solving these equations is typically not too computationally intensive. What is really intensive is to find these activation barriers that go into these equations. And especially you need then to locate the transition state of such an elementary step, like, for example, CO2 dissociation, which is quite expensive computationally. And then also getting all of the intermediates here, the structure and energy of these is also rather expensive. So how can we calculate these? So one option is to use density functional theory. So with the proper settings, this can be quite accurate for these metal catalysts here. The problem is that it's computationally also very expensive. Now, sort of to speed things up for screening. So I mentioned people have typically relied on these linear scaling relations, which are extremely quick because they're just a linear function, but they can also sometimes not be accurate enough. So what could we do instead? We could use a machine learning potential, and that we can use in more or less the same way as DFT. So we can get the forces from the gradient here, and we can do relaxations, transition states, optimizations in the machine learning potential as well. Of course, this requires some DFT data to train the model. And if we have a properly trained model, so in domain, we can also get almost DFT accuracy with these approaches at a much lower computational cost. Now, we have also been working with sort of some intermediate type models that are more similar to scaling relations, in that we aim to here directly predict an energy like an absorption energy or transition state energy. But we do that not with a linear model, but with a more complex nonlinear machine learning model. And we have been particularly experimenting with some graph representations. This is work that I started back in Munich together with Wenbin and Carsten Reuter. And the model we developed back then, basically the input it takes is the clean surface and whatever molecule. This was for absorption energies we were interested in. And then you can sort of decide what binding motif at the catalyst surface you're interested in. So, for example, to calculate the binding through the carbon atom here, and construct a graph representations where the edges in the graph here then represent how the molecules is bound to the surface. And then we have also some node features in our models. So these are features that we calculate for the clean surface and for the gas phase molecules to keep the cost low. So this can be sort of anything you can think of, any kind of descriptor that previous literature works have found to be related to absorption energies, for example, the famous D-band center. And then we need a data set to train these models. They are quite data efficient, so typically some hundreds or thousands of data points are sufficient. And we use a Gaussian process regression model here. And then we need a graph kernel also for that model, where we rely on this previously published Wasserstein, Weisweiler-Lehmann graph kernel to, in the end, provide a similarity measure when you take two graphs comparing how different or similar is it to what you have in the training data, which then allows you to get sort of a direct energy prediction of the absorption energy. So this was sort of the original model we developed back then, and we tested it on some rather complex molecules. Generally, the more complex molecules, the more the advantage of the scaling relations. Now, in subsequent work in Aarhus, that is mainly been led by my postdoc Raphael, we also extended now this model to be able to predict transition state energies. So it is more or less the same model. The only sort of difference when you want to do a transition state is that here it is not so obvious where the bonds are, how are things connected, because you have some bonds that are being broken in the transition state. So what we did here is simply for the transition state graph here to take the union of the edges that are present in the initial state and in the final state, which we know because these are sort of relaxed structures. And this turned out to work quite well. Now, Raphael has been applying this model to do some actual catalyst screening, and the reaction we were interested in here is the reverse water gas shift reaction, so CO2 hydrogenation to CO and water. And already this reaction network is quite complex. You have of course, adsorption-desorption reactions, but then you have also different possible mechanisms. You could have direct CO2 dissociation. You can have hydrogen-assisted pathway where you first form COOH, for example, or you could form HCOO, form it. So essentially, we took into account all of these different possibilities for the mechanism, and Raphael constructed a data set of adsorption and transition state energies on some metals and single atom alloys to train such models here. And the way we then assess the performance of our model is that we have our DFT calculated data set here that we then split into test set and train set. We do that 5 times through cross-validation. And then we can also, since these models are very cheap to train and to apply, we can also train an ensemble of models simply by subsampling our training data set. And that allows us then to get not just one energy prediction, but an ensemble of energies. So we can also get an uncertainty from the standard deviation of that ensemble. And what we found is that the predictions of this test set could significantly improve if we included just 3 of the simple species, the CO, hydrogen, oxygen, in the training data for these new materials, which is still quite a speed up, considering that you have all these intermediates and transition states in the end that you're trying to predict. And after we have sort of confirmed that the model works, we can then use it to extrapolate to new materials where we don't have any DFT calculations. So this work we selected some different materials that had found to be stable in previous literature works and also active, at least for this reaction H2 splitting here. So we knew they were somehow reasonable materials to try to predict. So first of all, let me show how the linear scaling relations work. So these data here are all the DFT data for all of these different reaction steps you have in the microkinetic model. And we did this on 2 different facets, 100 and 111. So you can see they generally follow a different scaling relation. This is well known in the literature. And all the green points here are the single atom alloys. So you can see that there are really some of these reaction steps where these are outliers from these scaling relations. And then there are also some where they actually follow quite nicely. And now, how do the machine learning model compare to the linear scaling relations? So here in this column here, you have the scaling relations for the adsorption energies and for transition state energies. And we get results that are very comparable to what previous literature studies. So typically, you get this mean absolute error around 0.2 EV for these. And the machine learning model does a little bit better. We can get the errors down to about 0.15, both adsorption energies and transition state energies, which may not sound like a lot, but one has to keep in mind that you plug this number into an exponential function in the end to get to the rates. So indeed, how does then these errors propagate into actually predicted turnover frequencies? So for this, we then did the full microkinetic model here to some relevant conditions, 500 VC, pressure of 1 atmosphere. And what you can see here are then all of the materials where we did the DFT calculations. So here, the yellow bar here is then the turnover frequency when we use DFT to get the input data for the microkinetic model. This is on a log scale, so you can see that there are sort of orders of magnitude difference between the different good catalysts in the predicted rates. The green ones here are the linear scaling relations, and the error bar here, as I said, comes from this ensemble of models that we train. Same thing goes from this graph-based machine learning model. So you can see both of these models can somehow capture trends, which are very good catalysts and which are really poor catalysts. You can a little bit better quantify the errors here in this parity plot of the rates. So on this violin plots here. So in general, we see that the linear scaling relations, when you look at how the errors propagate to the turnover frequencies, you get the mean absolute errors around a little bit less than 2 orders of magnitude in the rates. Whereas with the machine learning model, we can push that down to a little less than 1 order of magnitude, which is still sort of good enough to screen materials. So and then as a next step, then we applied the machine learning model to all of these other materials where we did not do any DFT calculations. And just to take out some trends from that screening. So, for example, nickel is one of the materials where we have DFT for it, and also it comes out quite active. This is well known in the literature. Unfortunately, this is also a catalyst that has some issues with selectivity, so it produces a lot of leasing. This is not something that's part of our microkinetic model, and it also has some issues with coking. It's also well known that copper is less active, but more selective to CO, and you have less of these coking issues with that. And then from the predictions of the model, we could identify a number of candidates that might be interesting to explore in experimental or more detailed theoretical work. So, for example, doping a copper surface with nickel or palladium with nickel, or there's these different combinations that might be good catalysts for balancing of activity and selectivity for this reaction. And some of these have also already been studied in the experimental works in the literature. Now, I told you that the most computationally intensive part is typically to find the transition state structure, and to get this huge DFT data set of transition states was actually a major computational investment. So in the next project here, we asked ourselves if there's a way to speed up this data collection process. And this is a project that Raphael carried out while he was visiting Jan Kitchen at Carnegie Mellon University. So here we used now a machine learning potential, and this is one of the state-of-the-art equivariant architectures from the Open Catalyst project, the ESEN architecture. And this is a pre-trained model. So this model has been trained on the OMAT 24 dataset, which is sort of again from the Open Catalyst project, one of these massive data sets with also non-equilibrium structures and in general materials spanning the entire periodic table more or less. It's then also subsample fine-tuned on some other data sets in the end. So we took this pre-trained model as our calculator. And then the first thing we were interested in is now we have an efficient calculator, we can really benchmark transition state search algorithms to find the most efficient way to locate transition states. And this, for the data set here, we picked 250 transition states from this previous work, where we already had done the full DFT optimization. And now here we were mainly interested in algorithms that work just on one structure at a time. So there are a couple of methods from the literature. There's a dimer method, ARPIS, and also this more recent Zeller method. So now we could basically, since doing machine learning single points is very cheap, we could establish these success curves, like on average, how many single point evaluation does it take to reach a given success rate. And from these three literature methods here, the Zeller method turned out to be the one that most that is sort of the fastest in getting to a high success rate. We also propose in this work a small modification to the Zeller algorithm, which we call the bond-aware Zeller, that brings up this success rate a little bit more. So what can go wrong in these optimization is, for example, for the dimer method, you can see some of the cases the molecule simply dissolved from the surface instead of converging onto a transition state. This method here, the ARPIS, some of them simply fail. You never converge to anything. And the main problem otherwise, for example, with the Zeller method is that you find a transition state, but it's not the one you were intending to find. You have sort of climbed up to a different transition state than the one that is connecting the initial and final state you're interested in. And this is mainly here where this EA Zeller method is a little bit more robust in that. So how does it work? So you start with a guess. This is sort of the original Zeller method. You start with a guess of the transition state structure, then you calculate an approximate Hessian with finite differences that you can then diagonalize to get the lowest eigenvalue mode. This is sort of the vector you see here. And then you can then optimize from here by decomposing the forces into directions parallel and perpendicular to that vector here. Do optimization steps and then update the Hessian along the way until you hopefully reach the convergence. So the sort of small modification that we did here is that for these surface reactions, you can define a vector, because you know what is the bond that you expect to break. You can define that vector, and then you can, to make it more robust, you can check whether that eigenvalue here is more or less in the direction of that bond, so by a dot product. So essentially, if this value is not below a threshold, then we do some small modifications to the Hessian, and this is then what sort of makes the model a little bit more robust in finding the transition states you're intending to find. Now we can also do that with other pre-trained machine learning potentials from the literature, for example, CHGNet, one of the Mie foundational models, or the UMA model. And you can see in all cases this bond-aware Zeller is more robust than the original Zeller algorithm. Now, what we more tried was, you can of course also do notched elastic band calculations, which is another optimization method where you optimize simultaneously a number, maybe 10 images along the reaction coordinate. And so as you can see, these NAP conjugations converge very slowly. Even if you do like 500 steps, then you have only found the transition state in like 70% of cases. And if you start from that guess, NAP optimized guess, it actually does not really improve your overall success rate. What we found to be the most promising approach was simply to stochastically do the optimization over and over again, where we did small random perturbation to both the guess structure of the transition state and the optimized setting. So if you with the cheap machine learning potential just do this over and over again, then you can push up the success rate to about 97% here for 20 restarts. So this then gives you a quite robust transition state identification. Still, of course, what about the accuracy? So this is a pre-trained machine learning potential, and it may not be DFT level accurate for these reactions. So it is actually not too bad. So in about 70% of cases, you can see the transition state that it has found in the optimization. If we do a DFT single point evaluation of it, then it's in about 70% of cases, we get something within 0.1 EV of the transition states that we found in our previous DFT work. And then the others are mainly higher in energy. So the next question is then, can we improve on that machine learning potential? And for this, we propose this active learning fine-tuning workflow here. And essentially, you start with the pre-trained machine learning potential to do the transition state search, which is what you see here. If you optimize until there's forces below a threshold, then you can do a DFT single point of that structure. And generally, since the model is not perfectly accurate, it will not be converted in DFT forces. But then what we can do is we can fine-tune our machine learning potential on the forces of that structure, and then do the optimization again with this new fine-tuned potential, and then sort of continue that until hopefully we converge and we have the transition state with DFT accuracy. So how efficient is that? Let me just sort of show you for comparison. If we do everything with DFT, so basically one transition state at a time, we do the full optimization with DFT, then on average, this costs about 100 DFT single points. Now, what you could also do is sort of, you could pre-optimize with the machine learning potential and then continue with DFT. That actually does not bring down the average cost that much. So what we found to be the most effective is this sequential active learning procedure. So basically what you do, you take one transition state at a time and you fine-tune your potential only to the forces of that transition state. And then you throw away the model, and then you sort of start over and over again fine-tuning from scratch every time. So that creates a highly specialized model. And the good news is that this is very efficient. You can then, on average, get the DFT quality transition state with only 8 DFT single point calculations. We tried also another approach where we call this batch active learning, where you are sort of fine-tuning on the entire collected transition states to sort of try to train a model that is maybe more general to work for all transition states. But that is actually not more efficient. The most efficient is to overfit essentially on one transition state at a time. And how does then the accuracy of this approach compare to? So if we compare, for example, if we do this optimization with DFT, as I mentioned before, with this bond aware seller method, you still have a couple of cases that fail. And this is then more or less the same. So basically, the robustness of this is more or less the same, whether you do it with DFT or you do it with this sequential active learning. Actually, you get a little bit higher percentage of match structures with this. So most importantly, where before we had a lot of structures that were much higher in energy compared to the previous DFT work, we can see that now in the majority of cases we get the same within 0.1 EV transition state, or even sometimes a lower transition state. So this is of course a very nice computational speed up here, a little bit more than an order of magnitude. One has to keep in mind, of course, that now we have also some other costs we have to do, especially the fine-tuning of the machine learning potential, which is done on the GPU. So also this workflow requires GPU resources, but still the sort of just in computational time, most of the time is still spent on the DFT single points, which is done on CPU. Okay, so this was sort of one project in the group about these alloys. So now I will shift gears a little bit and move into a completely other types of catalyst for the remaining part of my talk. And this is some work we have done on these inverse catalysts. So what you would call a conventional catalyst. Typically, you have a metal nanoparticle on an oxide support, and an inverse catalyst is then when you have an oxide on a metal surface. And the reason we're interested in these is that there are some experimental works that show that they can be quite active and selective, especially for producing methanol. So this is some surface science experiments where they have synthesized both of the conventional and the inverse configuration, and generally found that the rates were higher on these inverse, especially this indium oxide clusters on copper on gold here, which is from this paper here. They found that this is both active, but maybe more importantly, it's very selective to methanol. And of course, the question is, why is that? So the systems we have been interested in have been mainly, of course, zinc oxide and copper is sort of the commercial methanol synthesis catalyst. So that is, of course, very interesting to study. Indium oxide is also a good catalyst. So these were sort of the metal oxide clusters we were interested in. And then apart from copper, we looked also at palladium and gold for comparison with different number of the metal atoms in the clusters and different number of oxygen atoms in the clusters. So the first part of this project, which was mainly carried out by Luke in his PhD, so he's now a postdoc in my group, is since these are much more complex material, first of all you have to ask what do they actually look like under reaction conditions. And for this, we need to do global structure optimization. And that is, we need to find global. We're also interested in low-lying local minima in such a potential energy surface, which in general is very high-dimensional and very complex. And same as for the transition state search, this is very expensive to explore with DFT. So we want to do this with machine learning potentials instead. And here we used an algorithm called GOFI, which is developed by Björk Hammer, who is a colleague at Aarhus University. That's an algorithm that combines an evolutionary algorithm with a Gaussian process regression model that is trained on DFT data that you acquire while you explore the potential energy surface. And in this work, as I said, we looked into copper, palladium, and gold as the metal supports, and then the zinc oxide and indium oxide. What you have here is sort of the size of the cluster, how many metal atoms in the zinc or indium oxide clusters. And the colors in these plots is how many oxygen atoms you have in the structures. So we combined this global structure optimization with ab initio thermodynamics, which allows us to create these basically phase diagrams. So on the x-axis here, we have the oxygen chemical potential, which you can relate to the experimental conditions. So typically for methanol synthesis, this is in CO2 and hydrogen. You have a rather reducing environment, so you are quite low in oxygen chemical potential. Whereas when you synthesize these catalysts, you would do that maybe in an O2 atmosphere, and then you're pretty high in oxygen chemical potential. So the red color here, the dark red, is zero oxygen. So this is just the pure metal clusters. And if we sort of focus on these, there were already some interesting observations from this data set regarding like how easy is it to oxygenate these clusters. So generally, if you compare zinc to indium, you can see that it's easier to oxidize zinc. So these oxidized clusters start becoming stable at lower chemical potential compared to the indium. And there's also a very strong effect of the metal support. So, for example, it's much easier to oxidize the clusters when you have palladium as a metal support compared to when followed by copper, and then the most difficult on gold. We could also get other trends from this data. So, for example, if you look into zinc oxide and copper. And you focus just on sort of this first transition from zero oxygen to an oxygenated structure. So you can see that these tripod motifs here are very stable for zinc oxide, and sort of the first cluster, oxygenated cluster to form is always sort of a cluster where you have these tripod motifs in it. Now, in the second part of this project, we are interested in going towards predicting the reactivity of these clusters and maybe eventually being able to compare to these experimental works that showed a high methanol selectivity. And this is work done also by Mie Andersen, who's a PhD student in my group. So here to do reactions, basically we want to do that with a machine learning potential. We have the same challenges as we had before. First of all, the CO2 hydrogenation reaction network is very complex, especially if you want to go all the way to methanol. Then you have many competing pathways, you have competing products also. So there's a lot of intermediates and transition states to consider. When you focus on these clusters, then another challenge is that you have a lot of different sites of these clusters where all of these reaction steps could potentially take place. And finally, if you want to do screening, then if you would of course maybe you would want to investigate many combinations of support metals and oxide clusters. So for now, we are focused only on this challenge 2 here. So we have fixed the reaction step to be this CO2 hydrogenation to form it. To form it, it can be detected in the experiment, so it is sort of pretty certain that this is the pathway that is followed on these catalysts, and in general, this is believed to be one of the key intermediates in this step. So this is why for now we are focused on this step here, and then we have fixed the combination to be copper and indium oxide clusters. And this was a work that was initiated while Luc was visiting the group of Johannes Kästner in Stuttgart. So for that reason, we did that with a machine learning architecture that is being developed in their group. It's called Gaussian Moment Neural Network. And so it's a neural network with a trainable representation that's based on Gaussian moments. You can look up the references here. And here we trained then a machine learning potential from scratch. And we did that by considering a range of different clusters, different sizes and stoichiometries, among those that were found to be stable under some given chemical potential in the previous work. And then we trained this potential on structures along this interpolated reaction coordinate from a hydrogen atom and a CO2 to form it. And the way we sort of quantify the accuracy of the machine learning potential is that we do the optimization in the machine learning potential to get that structure. And then from there, we can also then continue optimizing in DFT to, in the end, get for comparison a DFT transition state. And what is worth to notice here, again, we do a DFT single point of the structure that was optimized in the model for this comparison. And basically, how we sort of divide in the data here. So the blue points here, what we call in sample, that's transition states at sites that were part of the training data, and out of sample here, then transition states at some new sites that the model had not been trained on. And you can see this is got a pretty good accuracy, mean absolute error around 40 millieV in both cases when we do the DFT single point evaluation. If you look at the actual energies predicted by the model, so for example, you look at the reaction coordinate here from CO2 and hydrogen to form it for one of these out of sample points here, you can see that the model generally has learned the potential energy surface quite well, and the structures are quite good. but there's still some shift in the energies, which is why we need to do this DFT single point evaluation of the structure here to really get the high accuracy. Now, with this potential, we were then able to make a rather large data set of transition states at these clusters. And when analyzing that data set, there were some interesting trends coming out. So, for example, the data generally divided into these two classes of transition states. So either you could have sort of, when you're more interior on the indium oxide cluster, you could have pathways where the hydrogen atom would sort of migrate over an indium atom before reacting with CO2. Or when you're more on an edge side of the cluster, you could also have pathways where the hydrogen atom migrated over the copper surface before attaching to CO2. And if you look at the distribution of activation energies, you can see that there's some overlap in the distribution, but generally the green ones here where you're over the copper atoms tend to have lower activation energies than the blue ones here, which is probably because hydrogen interacts a little stronger with the copper than it does with indium. And another interesting observation we could do based on this data set was, again, we can try to construct these linear scaling relations. Here we divided them up into the two classes with the hydrogen going over the indium or not going over the copper. So again, what you see here in this plot is this Brønsted-Evans Polarny relation. We're relating the activation energy to the reaction energy. Over here, it's sort of a different type of transition state scaling relation. But sort of the important point here is that no matter how we plot it, then basically the correlation is not very good. So these materials basically do not follow linear scaling relations. Up to the case of the single atom alloys, that was sort of the first example that I showed you, where we also had this sort of points that could break these linear scaling relations. So again, this is of course a very interesting observation for catalysis, because it basically means with these type of materials, you could hope to be able to design catalysts that would go beyond this maximum Sabatier optimum in the rate. So maybe that could be one of the reasons that these have been found to be quite promising catalysts in the experiments. But for that to really be sure of that, of course, you would need to do more a full microkinetic model. Now, with this, I reached the conclusions of my talk. So I hope I convinced you that machine learning methods can be helpful that they can drastically reduce the computational cost for many of the tasks we have in catalysis modeling, like structure prediction or predicting absorption energies and transition state energies. And we're at a point now where you can basically start doing screening with full microkinetic models without relying on these simpler linear models for the input parameters, but simply relying on machine learning instead. And if you can get models that can predict absorption energies and transition state energies at a low enough cost, this means that you can now also do quite detailed microkinetic models where you take into account, for example, competing reaction pathways, such as maybe on some metals, the dominant reaction pathway is the direct CO dissociation, but on other metals or alloys, maybe it's some hydrogen-assisted pathway. And what we also saw from our data that when you go beyond these sort of simple crystalline metal facets, then it seems to be the rule more than the exception that the more complex materials break these linear scaling relations. So we saw that for the single atom alloys and for the inverse catalysts. And maybe this is one of the keys to designing catalysts that are more active and selective. So with this, I reached the end of my talk. Thank you very much for your attention. I would also like to thank for the funding behind this work, and I hope you have some good questions.
Thank you, Mie, for the inside-out demonstration of such, very insightful cases. Are there questions or comments? So just feel free to unmute yourself and ask the question. Or you can also raise your hand, I can monitor. If your microphone doesn't work, you can type also your question in the chat. So then while the others are getting themselves prepared, I have two questions actually. So then for the oxide clusters supported on metallic substrates, the last part you talked about. So then what is the challenge to use such universal machine learning internal potentials here actually?
That's something we are also working on now. So you sort of have the choice either to train the machine learning potential from scratch, which is your own data, or to start from some pre-trained model.
Mm-hmm.
And I cannot tell you sort of what is the most promising right now. We are trying both things. And I think for some systems, these pre-trained models are at a level of accuracy now where you could even start doing some screening just with the models because they might be good enough to give you rough trends. Does it look like a promising catalyst or not? As
Mm-hmm.
you might want to do more detailed modeling to really sort of get the details right.
Yeah, but I remember seeing recently a review paper from your group talking about the applicability of such universal potentials on the catalytic properties, right?
Yeah.
So in this regard, in particular for the transition state modeling, so there, such states are far away from, or if not far, very far, but away from the equilibrium states. And then those configurations are not normally included in the training set. So then do you think there's kind of a strategy? I mean, you mentioned such active learning. I think this is very interesting. But then in this regard, my question would be, the universal potentials without fine-tuning, how accurate can it be for the transition state prediction?
Yeah, I mean, as I showed you, go back. Okay, that's a lot of slides back, but
Yeah.
I showed you sort of how accurate are they out of the box for something like a reaction on a metal surface. So
Mm-hmm.
simple adsorbate on metals, and there you're sort of already at about 70% of cases you can get the transition state within 0.1 eV of DFT, which is not bad, I would say. But this is of course also for exactly the systems that the sort of most training data available for. So we
Mm-hmm.
have done some tests also for oxides where generally the performance is not so great. So I think it's really a big challenge in the field right now. How do you sample the right data to do, for example, transition state, as you say, which are these high energy structures?
Yeah.
And I don't know if anyone has solved that yet, but
Mm-hmm.
it's definitely a hard problem.
Fantastic. Good to know. And then I think I have seen a few colleagues from industry registered for this seminar. And then I want to pretend that I'm someone from industry and ask this question. I think for the single atom catalyst, they are very interesting for scientific research. But I heard that it's very challenging to get such kind of catalyst used in real life. So what is your take on this point? And also, on the other hand, I think recently people are talking a lot about the high entropy materials, like either alloys or oxides for catalytic properties. So then this is another extreme case, where we can play with the chemical compositions. So what is your vision or your take on such two extreme cases for real life applications?
Well, I think for industry, the main problem is stability. So
Mhm.
also for these metal oxide interfaces, for these inverse catalysts, I think stability might be a problem if you want to scale this up in industry. I'm not really myself working on that, but that is sort of the feeling I get. So to be honest, in these works, we are sort of more interested in understanding fundamental questions about how catalysis works. What does it take to get an active more than we're interested in scaling this up. But maybe among the works that we did that I think is most promising to industry, we did some work on zirconia, and that is actually an extremely stable material. I think it's already being commercially used. So these doped zirconia, there was some years ago a quite impactful experimental paper where they showed that not only are they selective, but they are also extremely stable under reaction conditions. So these are maybe some of the catalysts that are most promising to use in industry. Yeah.
I see. So basically, then we need some really very well controlled approaches to engineer such materials, particularly such crystalline environments, if we want to use such kind of, let's say, single atom catalyst.
Yeah, I'm not really an expert in how you you make these stable enough to for industrial application.
I see. Okay, thanks. Are there any questions from the audience? Everybody cannot wait to try out with the machine learning E-type potentials? Okay, good. I do not see any raised hands or someone unmute themselves. Okay, good. So then, thanks again for this very insightful presentation. I have learned a lot. The most important take-home message for me is that using the potentials, we can now tackle the transition states. I think this is quite interesting to me. Not to mention such interstellar catalytic or catalysis. This is really beyond my imagination. Thanks a lot.